What's the difference between molality and molarity? What is the difference between molarity and molality? Just by remembering the definitions of the two different measures. Do you remember what those are? Let's go ahead and just write out the formulas for both. So capital M, trying to exaggerate that point by putting the 2 feet on the bottom there. Capital M and lowercase m. This is the symbol for molarity, and this is the symbol for molality. Okay, so what are the formulas for the two? How do we compute molarity and molality? Go ahead, Ray.
Molarity is moles of solute over liters of solution.
Okay, somebody else want to do molality?
The number of moles, or number of moles solute over the number of kilograms solvent.
Right. So remember those definitions. The molarity is moles. So they both have moles of solute on the top. Both of these measures are asking how much of the, in the example, the salt, the solute, the thing you're dissolving into the solvent, how much of that do you have? And they both do it in moles. So that's the easy part. Moles of whatever you're putting in to be dissolved goes on the top, is the numerator. The differences are in the denominator. Remember that molarity is looking at what is the volume of your total mixture, your whole solution. That includes both the solvent and the solute together. What volume do they take up? In molality, it's how many kilograms of solvent do you have, okay? In the case of molarity, when I have a glass of water and I keep adding salt to it, I'm changing the volume of the total solution. In molality, I start with a certain amount of water, and no matter how much I add, I don't change the denominator. I only change the numerator. As I add salt, it makes the top go bigger, but the bottom stays the same. In this one, as I add more volume, I'm going to increase the moles of solute dramatically, but I'm also going to slightly increase the volume of the solution as well. They're slightly different things. Okay. So this one is beneficial in that if I know what I'm driving toward, and I have a certain amount of solvent already, it's just a matter of adding more to get to the right molality. I can compute that and figure that out and just keep adding till I get to the right point. With molarity, as I add a little bit, yeah, I'm increasing the numerator, but I'm also changing the volume. And that's going to, I have to continually be recomputing that in a different way. So molarity and molality. Molarity is the volume of the solution, the volume of the whole. Molality is the mass of the solvent, which generally in your equation will not change. This one will, or could. So any questions on number 12? That was a pretty straightforward definition, right? You see? So it really just comes down to, for some of you, just have to memorize the definitions or the formulas. Don't get tied up also at the liters of solution. Some people like to try to figure out, well, it's this much for this much, then what is it per liter? Just take whatever the moles you have and divide it by whatever the volume you have. Okay? Some people get really wrapped around, it's this per liter, but I don't have a liter. I've got this much in this volume. Do the math, it'll work out per liter. Okay. Definitions of molarity and molality. The second question there for today, review question number 13, says if you wanted to protect water from freezing, which compound would accomplish this the best? And it gives you some compounds there. Now, notice those compounds. What do they have in common? Okay, they all have nitrates in them. They're all NO3s. So since they all have nitrates in them, what kind of molecules are they? What is an NO3 molecule? We've studied it before as a polyatomic ion, right? Let's go ahead and just look at the first one there, sodium nitrate, NaNO3. Let's dissolve, metaphorically, let's just imagine we're dissolving this molecule in water. What is it going to dissolve down into? Well, first of all, what kind of a molecule is this now? since this is a polyatomic ion, this is an ionic compound. There's an ionic bond, there's an attraction between the positively charged sodium and the negatively charged net charge for the nitrate polyatomic ion. When we put this in water, the ionics break apart, right? So as this dissolves in water, it's going to decompose. If we think of it as a reaction, which it's not a reaction, but if you think of it like a reaction, this would decompose into sodium and the nitrate. This is an ion, this is an ion, correct? Now at this point, we said that ionic compounds break down into the individual ions. Some people want to go ahead and push this even farther and say, well, this will break down more, won't it? But what have we already said about covalent molecules? Do they break down any more? No, they don't. So this is where the reaction stops. This ion and this ion, they stay together. Why? Because there's a bonding there. There's a sharing of electrons that they're not willing to give up. So each individual polyatomic ion will be surrounded by water, or whatever the solvent is, and every sodium ion will be surrounded by water, or whatever the solvent is. So it'll dissolve to this point and go no further. Right? So how many pieces does this molecule break into? It breaks into 2 pieces. So my I, if I use this molecule, is 2. Did you see that? Go to the next one. It's magnesium nitrate. If I change this to an Mg, and then it's NO3 sub 2, what is this going to break down into? Well, in the same way, using the same logic, this is going to break down to magnesium, a nitrate, and another nitrate. Do you see that? So this is the dissolved form of this molecule. All the ionic bonds separate, the ionic attractions, they separate, but the covalents stay in place. So this will dissolve into this. What would the I be for this? 3. So using your delta T equals negative I K sub Fm, the I would be 3. The last case is aluminum nitrate. Dissolve into an aluminum and 3 nitrates. So my I here would be 4. Now using the formula delta T equals negative I K sub F M. If I have to pick one of these molecules to use, and I want to have the greatest protection, that means I want my delta T to be as large as possible. Does that logical step make sense? To have the greatest protection, I need the freezing point to go as low as possible. You know, you go to the store and you buy different kinds of antifreeze for your car, or maybe better, different kinds of windshield washer fluid for your car. You know, if you buy the summer mix, the first time it gets cold, that thing plugs up and you're not going to have any windshield wiper to wipe that brine off your window. So you have to, in the winter, buy different window cleaner that has a lower freezing point. You want to protect your system, get the freezing point as low as possible. Here, you want to protect your water from freezing. Which would you use? I want to get something that's going to make that delta T negative but big as possible. How do I make it as big as possible? Well, my K sub F is the constant for my solvent. My solvent's water, so this is going to be constant, right? So the way I can affect how I change my delta T is by affecting the I that I use and the molality of whatever mixture I mix up. So how do I make this as big as possible, protect it as much as possible? I can make that I as big as possible. Of those 3 molecules, which one has the largest I value? Aluminum nitrate. It has an I value of 4. What that means is I can have a much lower molality if I use aluminum nitrate to get the same change in temperature. I need little of it, as opposed to I need, you know, if I had one that had the I2, like in the case of sodium nitrate, I would need double its molality of sodium nitrate to get the same effect as the aluminum nitrate, because the I value is double that of sodium nitrate. Okay. So trying to make delta T as big as possible, how do I do that? I find these variables. This one is constant. So I either have to make a stronger molality, or I choose a molecule that breaks up into the most number of pieces. Aluminum nitrate of those three breaks up in the most number of pieces and gives me better water protection from freezing, because it gives me a greater delta T, because it breaks into 4 pieces. All right. In that vein, well, actually, we have time to do all 4 of the practice problems, so that's fine. So any questions on the logic behind this? Is just a logic question. There's no math here to do. Just looking at what you're trying to accomplish. Trying to accomplish by getting the greatest delta T that you can. Remember, too, that negative is really a -1 times this stuff. You don't get a negative I. I think I might have said that before class when I was in a little bit of a heightened state, okay? But this negative I, the I is going to be a positive number. 1, 2, 3, 4. Remember, it's always 1 for covalence because they don't break down. Each molecule breaks down. And maybe a way to think of the I is this. When the solvent dissolves, how many pieces does each molecule break into? For covalent, each molecule, it doesn't break into anything. It stays as 1 piece. Okay? For sodium chloride, 2 ions, it breaks into 2. And so on. So to think of the I as how many pieces does each molecule dissolve into? What does it become? How many pieces? And for covalence, it's always going to be 1. If there are no questions, we'll go on to practice problem number 6. Practice problem number 6 says that if a solution is made by mixing 75 moles potassium hydroxide mixing 75 moles of potassium hydroxide with 4.5 kilograms of water, what is its molality? They've given you everything in the right form you need already, right? The molality is the moles of solute divided by the kilograms of solvent. So they give you all the numbers in order. And the math comes out to be 16.7. If you did the math, you recognize it was 16.6 repeating, 16 2/3. So then we go back to chapter 1 and say, how many significant figures do I have? I've got 3 significant divided by 3 significant. The least number is 3 significant. So my answer is to 3 significant, which means 16.67, and then I rounded up the third. Right, so this is pretty straightforward. They gave you everything in the right form. But on number 7, they add one more learning step. If a solution is made by mixing 70 grams of calcium bromide solution is made by mixing 70 grams of calcium bromide with 1,314 grams of water, which becomes, we're going to put it in the right form, 1.314 kilograms of water. What is the solution's molality? Now we have 70 grams. Is that what's supposed to be in the numerator? Is that where? No. But in our solution diagram, remember the solution diagram is going to help you even if you're not using a reaction equation. Solution diagram, remember if we did a vertical line in our solution diagram? What are the different places for each of that pieces of information? Here's where the reaction formula would be up on top, right? And we're looking at one particular molecule right here. We have this vertical line. What are the different locations? What do they involve? Well, here it's the mass, the molar mass, the moles, the molarity, and the volume. Okay. So I have the volume, I multiply it by the molarity, I get the number of moles. If I have the mass and I divide it by the molar mass, I get the number of moles. I need the number of moles, and I have the mass. How do we go from mass to moles? I divide by the molar mass. So the molar mass of of the calcium bromide, I have that down as 199.9. So 70 grams divided by the molar mass of 199.9 grams per mole is going to give me how many moles of calcium bromide I have. The moles divided by the mass of the solvent here in kilograms, the water, and the answer is 0.266 molality. Significant figures, again, 3 is my lowest number, so I carried out the 3 places. Okay. So I know I kind of just read it and wrote it in place, but remember our molality is equal to the number of moles solute per kilograms solvent. Moles of solute is the same as the mass of solute divided by the molar mass of the solute. And the mass in kilograms of the solvent produces our molality. So 6 and 7, pretty straightforward. Just using the formula and knowing how to get to those places. And just so you know, even at home when Will might have a question occasionally, I'll just say, what does the solution pathway take you? How does it go? You have a mass, you're looking for moles, what do you need? I have to pass through molar mass. So you need to get that number. What's the operation? I'm going down, it's division. Going up, it's multiplication. Okay? So if I have a volume and I know the molarity, I can compute the moles, and with the moles given the molar mass, I can compute the mass. Just have to go through each step, knowing that up is multiplication, down is division. Okay? Yes, sir. You need to go. You need to go. Mm-hmm. Actually, about 5 minutes late. I did too until just now, but it's a good time for you to go. So get out of here. Doctors or orthodontics or dentist or? Okay. So questions on how to solve these? Anyone? Number 8. If you want to lower water's freezing point by 18 degrees Celsius, what pieces of information do we have just in that phrase? If you want to lower water's freezing point by 18 degrees Celsius. So your delta T, what do you see in there, Ray?
What we're trying to get to?
Right. You want to lower it by 18 degrees, right? So your delta T is going to be negative 18 degrees Celsius. Okay. What else do we?
Adding that to the given
Right, but the other piece in here, just listen to the words. If you want to lower water's freezing point, what's our solvent? Water. Okay, so I don't want you to assume it's always going to be water, because it'd be really nasty of them to put on the test. You dissolve in acetone, which has a freezing point of whatever the freezing point of acetone is. You're going, oh, I've never had to deal with that before. Okay? So your delta T is going to be negative 18 degrees. Your solvent is water. Now, you don't need to write this down, but the way I look at that, my T initial for my freezing point for my solvent is 0 degrees, right? It's 0 degrees because it's water, not because we always use 0 degrees. Before I add anything to it, my solvent's going to freeze at 0 degrees Celsius. Again, you haven't been prepped on how to do this, but just this is part of the logic behind it. Just it normally freezes at 0. So if I think that my T for freezing is going to equal my T for freezing initial plus my delta T. It's going to freeze at whatever it used to freeze at plus whatever the change in temperature that I compute. I want to compute that delta T to be negative 18 degrees. I want to lower the freezing point by 18 degrees. So if you want to lower the water's freezing point by 18 degrees by adding sodium chloride, so my solvent is H2O. My solute is sodium chloride. If you want to lower water's freezing point by 18 degrees by adding sodium chloride, what must the molarity of the salt solution be? Molality equals question mark. Okay. So how am I going to figure out this? How am I going to figure out the molality given that I have a solvent and a solute and a delta T that I'm looking for? Hopefully you know it's the one formula we have that looks for change in temperature, right? So let's go ahead and throw that formula up here. Delta T equals negative 1 I K sub F M. Now I don't put the little X's between them like they do in the book because to me that's confusing. The little multiplication signs. Hopefully you get to the place where you know that the multiplication signs, okay? Maybe your progression in math looks something like this. Delta T equals negative I times K sub F times M, which later becomes delta T equals negative I dot K sub F dot M, which later becomes delta T equals negative I, parentheses, K sub F M, which eventually becomes this. Okay? This times this times this. Oh, this times this times this. Oh, this times this times this. And we finally get to the place where we can see it just by writing it like that. So, what are we solving for? What have we asked for? Molality, right? Do we have delta T? Yes. Do we have I? No, but we can figure it out real quick. Do we have K sub F? Yes, we do. So we have everything except what we're solving for, molality. So let's take the equation and rearrange it to solve for molality. Two ways to do that. The shortcut is, since it's pure multiplication, is to take whatever is not, we need to get our variable alone on that side of the equal sign. Take everything that's not that variable and move it to the other side of the equal sign. The shortcut would be just to take this whole block here and slide it underneath, so we get delta T divided by negative I K sub F equals M. Algebra 3 folks are going, yeah. Algebra 2 folks are going, okay. If that's a little bit too shortcutty for you, the long way to think of that is take and divide both sides by everything that you're trying to get rid of, which would be negative I K sub F. That'll leave M all by itself. But in order to stick to the rules and not change the value, I need to do the same thing to both sides, negative I k sub f. So I divide both sides by negative I k sub f, which this cancels this, and you end up with the same thing. Okay? So my molality is equal to delta T over negative I k sub f. The delta T is negative 18. I'm going to lower it, negative sign, 18 degrees. So my delta T is negative 18 degrees Celsius. Divided by a negative, it's not negative I, it's negative 1 times I. Negative, what is I? I is what does one molecule of your solute divide into when it dissolves? Sodium chloride, 2 ions. So I becomes 2. Now here I can't just keep writing numbers, can I? I'm going to go ahead and bracket that negative within the 2. K sub f, it's water. We've used this many times. It will still be provided to you, but it is 1.86 degrees Celsius per molality. Remember, degrees Celsius per molality is a derived unit. Why? Because when I'm done, my units have to be in molality. The Celsius cancels the Celsius, and molality is left as my ending unit. So it's negative divided by negative is a positive. So you can say that those cancel each other out, however you think of that. Negative divided by negative, we do the math. 18 divided by the quantity of 2 times 1.86, or 3.72. Okay, so we do that math, and I came up with a molality of 4.8. Again, because this is an integer, it's exact, doesn't affect your significant figures. 1.86 has 3 significant figures, but 18 degrees Celsius only has 2 significant figures, so my answer has 2 significant figures, 4.8 molality. Was there a point on here where, for those of you that didn't get this, was it a conceptual thing? Do you have it now? Or is there still a place where you're stuck? I gave a this or that with no responses, so I should only give one of them, right? Do you feel, we're going to be doing number 9, which is same type of thing, approximately the same, but are there any questions remaining on question number 8? Do you see what you didn't understand before? Okay? Go ahead, Ray.
So what if the solvent wasn't water? Like,
Okay.
will it give it to us?
If it's not water, they're going to have to give you the K sub F.
Okay.
And they're going to have to give you the freezing point too if they ask for the, what's the new freezing point? They'd have to give you the freezing point of the pure solvent, and they would have to give you the K sub F for that solvent. There's just, every solvent has its own unique freezing point and its own unique K sub F. So for you to memorize them, that's ridiculous. In college chem, they would give you tables and you have to find it. At least that's the way it was in the old days when we actually used real paper and real ink. Today you just Google it. Or you, Siri, what is the, you keep it quiet so the teacher doesn't hear you asking during the test. So you can write down your answer. You know, I'm a systems engineer, so I enjoy looking for pieces like devices that disable all phones and things in the building. I think it would be really cool is things would make them fry or blow up. Wouldn't that be cool? What's the matter? My wrist is hot. Why? Ah! It's a serious problem in schools. I mean, they're hiring consultants and resource agents just to remove electrocommunication devices from students who are pretty adept at figuring out how to cheat together on exams. So that's why they have to start checking wrists on the ACTs now for everybody that comes in. Number 9, shall we? What is the freezing point of a solution made by mixing 42 grams of NH3, ammonia, not ammonium, NH4 is ammonium, with 420 grams of water. Notice on the problem they give you the K sub F there of 1.86 degrees Celsius per molality. That's the K sub F of water. You could just go ahead and write it down there. So what's the new freezing point of this water that has this much solute in it? There's another way to say the problem. What is the new freezing point of water that has 42 grams of ammonia in it? We look at the formula delta T equals negative 1 I K sub F M. What is I equal to in this problem? Look at your solute. One molecule of solute. How many parts does one molecule of solute break down into when it dissolves? What kind of a molecule is it? NH3? NH3 is a covalent molecule. NH4 is a polyatomic ion. But NH3, ammonia, is a covalent molecule. All covalent molecules stay together. So one molecule of solute dissolves and stays one molecule when it dissolves. So your I is going to be equal to 1. K sub F, we've been given 1.86 degrees Celsius per molality. And molality, we need that for our formula as well. What is molality? It's the moles solute divided by kilograms of solvent. Right? That's our definition. Do we have moles of solute? No. We have mass of solute. How do we get moles when I have mass? Mass divided by the molar mass gives me moles, right? Let me rewrite this formula and say that molality equals mass divided by the molar mass of the solute divided by kilograms of solvent. Because the mass divided by the molar mass is another way of saying the moles. Mass divided by the molar mass is going to give me moles. Molality equals the mass of the solute that I have, 42.0 grams, divided by the molar mass of NH3. Molar mass, just 17.0 grams per mole. How do I come up with that? I take the mass of 1 nitrogen and 3 hydrogens, I add them together. That mass in AMUs is the mass of one molecule. That mass in grams is the mass of 1 mole of that molecule. So 17 grams per mole divided by the kilograms of solvent. I've been given 420 grams. How would I write that in terms of kilograms? I have to move it 3 places to the left, right? 1, 2, 3. Kilograms are greater than grams, so when I go to a greater unit, I need to go to a smaller number to keep it the same. 1, 2, 3, 0.4, so it's 0.420 kilograms of water. That math comes out to be 5.88. A 5.88 molality. So in order to compute a new freezing point, I need to know the change in temperature. In order to compute the change in temperature, I need to know an I value, a K sub F value, and an M value. Here's my I value, here's my K sub F value, and here's my M value. Now I can work the formula to figure out delta T. Delta T equals negative 1. Okay, higher math, I'm just going to write the negative, right? Because this is already negative 1 times whatever I is. So negative 1 times 1 is the negative sign. 1. Okay, just so I don't lose some people, there we go. How's that? Thank you for smiling, Algebra 3 people. I appreciate it. So negative 1, K sub F, 1.86. I'm dropping the units now because we know the units are going to work, but we could write them off to the side here. It would be degrees Celsius per molality for this, and M is going to be molality, which will give us degrees Celsius. So what is the molality? 5.88. My delta T then comes out to be negative 10.9. Negative 10.9 degrees Celsius. It's my change in temperature. When I'm looking at the change in temperature, and the question says, what's the freezing point of the solution? To get the new freezing point, I need to take the old freezing point and add this to it, add the negative number. The old freezing point, because it was water, was 0. When I add a negative 10.9 to that, I get negative 10.9. So the new freezing point is negative 10.9 degrees Celsius. Hypothetically, if this solvent, if it weren't water, everything was the same, but it weren't water, it would have had a freezing point of negative 10 degrees Celsius. What would the new freezing point be? If the original was negative 10, what would the new freezing point be? Pardon? If the old freezing point was negative 10, if the pure solvent freezes at negative 10 degrees Celsius, what would the new freezing point be with the ammonia in it? If it froze at negative 10, the new freezing point would be negative 20.9. Why? Because the delta T is negative 10.9. So think of it this way. The temperature to freeze equals the temperature to freeze initially. What was it with nothing in it? Plus my delta T. The temperature to freeze is going to be my initial freezing point. And I said, if it froze, whatever it froze at negative 10 degrees. And I have to add my delta T to it. It's negative 10 minus 10.9, or a new freezing point of negative 20.9. Again, reiterate this because I don't want you to think that your new freezing point is always going to be whatever you compute as your delta T. The only reason that's the case is because we tend to use water, and water has an initial freezing point of 0. So 0 minus your delta T is the same number as your delta T. But if you have something other than water, it's not going to be the same thing as your delta T. It's going to be your initial freezing point plus your delta T. It's going to be a negative number too, so it's plus a negative, which means subtraction. The original minus the negative of your delta T, or 0 plus, or excuse me, your initial plus delta T. So if your original froze at negative 10, your new would be negative 20.9. If your original was negative 5, your new would be negative 15.9. If your original was 5, your current would be negative 5.9. See that? You have to put in whatever the initial was. Some of you were good until I went positive on you there. Let me go to this. Let's say that the original freezing point of a pure solvent was 5 degrees. If it was 5 degrees and my delta T is 10.9, my delta T is negative 10.9, my new freezing point would be negative 5.9. You see it? Wherever your original freezing point was, and then move to the left with the number you calculate.